So, welcome back. And this is our penultimate session of the FTP. And uh, we were discussing about various machine learning techniques, and it is time to move to the topic what the architecture, the hardware architecture needed for this kind of machine learning training, testing, all these activities. Uh, so, the topic of the session is high performance computing architecture for scalable AI and data processing. And the expert faculty for the session is Dr. Chilankamol. She is MDS software system design engineer working at AMD India Private Limited, Bengaluru. We are quite proud to announce that he has been a student of Rajiv Gandhi Institute of Technology, Department of Computer Science and Engineering. In fact, she was one of the brightest students of our MTech degree course. And with all pleasure, I would like to welcome Dr. Chilankamol Sunny. After completing her MTech from Rajiv Gandhi Institute of Technology, she completed her PhD from IIT Palakkad. And with all pleasure, let me welcome Dr. Chilankamol Sunny to your alma mater, not as a student, this time as a resource person. Thank you.
Yeah, thank you, sir. Thank you for the kind words. And it's an honor and a privilege to be part of this program, which is organized by the Department of CSC from RIT. Okay, I hope I can start now.
Yeah, sure.
Hope my screen is visible.
Yes.
Okay. Good afternoon, everyone, and welcome to this session on high-performance computing architectures for scalable AI and data processing. Before going into the technical details, let me first set the context. We are living in a time where artificial intelligence is pushing the boundaries of what our computing infrastructure can handle. And HPC is becoming central to meeting those demands. And that's the motivation behind choosing this topic. I've planned this session as a mix of conceptual understanding, real world trends, and practical examples. So by the end, you will be able to connect the HPC concepts directly to AI applications. So in the next 90 minutes, we will cover a high-level context and why HPC is so important for AI and large-scale data workloads. And then we'll see the key HPC architectures and how they're evolving, how accelerators like GPUs, TPUs, and custom silicon fit in. We'll also see the performance optimization techniques, including the programming model strategies. And finally, a hands-on demo of measuring performance on a simulated HPC set. But what is HPC? The HPC refers to computing at the highest possible performance levels, not just the raw speed, but also the ability to scale workloads across thousands of compute nodes efficiently. And in AI, HPC enables training large-scale models like GPT, stable diffusion, and multimodal systems that would otherwise take years to train on conventional systems. Coming to inference, HPC supports in critical applications, for example, healthcare diagnostics, where you need immediate results on high-resolution images. It accelerates data pre-processing, which is often the bottleneck in AI pipelines. In data processing, HPC powers the big data analytics, enabling businesses to derive insights from petabyte-scale datasets. So it's essential in scientific computing, where we simulate weather patterns, molecular interactions, and astrophysical events. But why HPC is so much important now? So here the graph highlights the exponential rise in both compute and memory requirements of AI models from 2019 to 2025. On the left, the blue bars show the compute in petaflop days, growing from just a few thousand for GPT-3 to nearly 40,000 projected for the future Model X. And on the right, the orange line shows the model size measured in billions of parameters, climbing from GPT-2's modest 1.5 billion to more than 1.5 trillion parameters expected by the end of this year. So the key message is that both compute and memory demands are scaling at rates far beyond what a single machine or even a small cluster can handle. This is why AI today depends on HPC techniques, the distributed training across thousands of GPUs, high bandwidth interconnects, and supercomputer class infrastructure similar to what traditional HPC has used for large scale simulations. Now it's important to understand that AI workloads are not just another HPC workload with a different label. They have unique characteristics. First of all, the nature of computation in AI, deep learning, especially in deep learning, most of the heavy lifting comes from dense linear algebra, metrics, and tensor multiplications. So these operations are highly regular and compute intensive, meaning that once the data is loaded, the GPU or the accelerator is kept busy with a high compute to IO ratio. In contrast, HPC workloads are more diverse. They include not only the dense matrix operation, but also sparse computation, simulations, graph algorithms, and also workloads with irregular access patterns. So this makes the memory access and communication overheads more critical in HPC than in AI. Coming to precision requirements, AI models are surprisingly tolerant to reduced numerical precision. Training and inference often use FP16 or even int8, which reduces both the computation time and the memory bandwidth requirements. Thanks to that. And in HPC applications such as scientific simulation usually require very high numerical accuracy. They rely on double precision arithmetic to ensure stability and correctness of results, especially when errors accumulate over billions of simulation steps. So next is the data movement. AI workloads can be more of a streaming or batch-oriented nature, where HPC workloads may require frequent all-tool communication between nodes. And the most important difference here is in the scalability pattern. In AI, scalability comes in the fashion of data parallelism, model parallelism, and pipeline parallelism. Let's see each of these in detail. So in data parallelism, we are splitting the training data into batches. The same model or the replica of the entire neural network is copied onto multiple processors or GPUs, and the split training data set, which is split into many batches, each processor will train on each such mini batches. After computing the gradients locally, processors synchronize and update the model parameters. And the use case is in training large models like ResNet and GPT, where data volume is huge, but model fit into a single device. There we see the data parallelism. Coming to model parallelism, when the model is too large to fit on a single GPU or a processor unit, we will split that into different parts. Let's say the layers, or even the subsets of layers of weights are split across multiple devices. And each processing unit will handle a portion of the forward and backward pass. It is like a car assembly line where one team makes the engine, another makes the chassis, and another will be installing the electronics, but together they are building a full car. It's just the same way. And the use case is where in very large neural networks like GPT-3 or 4 with hundreds of billions of parameters. Pipeline parallelism is kind of a model parallelism where the model's layers are divided into stages and micro batches of data flow through them in a pipeline. Let's say while stage 1 is processing microbatch A on one processing unit, stage 2 can simultaneously be processed, can process microbatch B on the next processing unit. So this way it goes. So here the advantage is that it keeps all the devices busy and reduces the idle time. Use case is the transformer training with pipeline engines like G-pipe or deep speed pipeline. But when it comes to HPC approaches, it is either the spatial scaling or the functional scaling or distributed memory scaling. So by spatial scaling, we say domain decomposition, which means the problem's domain is partitioned into subdomains and assigned to different processes. And each processor will be solving its local part and then exchange on the boundary or the overlap information with the neighbors to maintain the correctness. For example, when we simulate weather over India, we'll partition the atmosphere grid into north, south, east, and west subdomains, and each node will solve its own subgrid problems. And it is called spatial scaling because the workload scales by cutting the space of the problem into parallel regions. So in task parallelism, what we do is the functional scaling. So different processes perform different tasks rather than the same one. For example, in a multi-physics simulation, one set of the processes can handle, let's say, the fluid flow, while another computes the heat transfer. And it's called functional scaling because parallelism comes from splitting the functions or the task instead of data. And in MPA-based scaling, the modern supercomputers uses distributed memory. And message processing interface or MPI is the standard for communication between these nodes, as you are all aware. And it allows the processors to send or receive data or broadcast or reduce or synchronize across thousands of processes. So it's called distributed memory scaling because MPI is what enables scaling across large clusters where memory is not shared. So as I summarize, we can say that in AI, parallelism is structured around how to split the model and data to exploit the GPU clusters. Whereas in HPC, the parallelism is structured around how to split the problem's domain and synchronize through MPI across distributed nodes. The challenges in both the worlds is balancing the compute and communication, the energy efficiency, since the power budgets are now a limiting factor, and optimizing for a heterogeneous mix of hardware while keeping the software portable. And understanding these differences between the AI and the traditional workload is key when designing HPC infrastructure to AI workloads to serve the AI workloads effectively. Now that we have set the context, let's dive into or let's discuss some core HPC concepts. First, we will see the HPC architectural components. So in modern HPC nodes, they're no longer CPU only. They integrate multiple compute elements. Let's say CPU remain essential for control heavy latency sensitive tasks and serial workloads. And GPUs dominate in AI training or inference due to thousands of cores and high memory bandwidth. And we also have specialized accelerators, ASICs, the application-specific ICs, which has the highest efficiency for fixed workloads, and FPGAs, which are reconfigurable for evolving algorithms, CGRAs, the coarse-grained reconfigurable arrays, a middle ground between FPGAs and ASICs offering programmable hardware-level parallelism. So these heterogeneous architectures like NVIDIA's Grace Hopper or AMD's MI 300 or Intel Ponte Vecchio, they maximize the throughput by matching the workloads to the best processing unit. So we'll assign the workload to the best matched processing unit. So that's the key here. Coming to the memory hierarchy in HPC, the HPC system rely on a multi-tiered memory hierarchy to balance the speed and capacity. At the top, we have the registers and cache, which are the fastest, but also the smallest. So they're ideal for immediate computation. So as we move down the hierarchy, we trade off the speed for capacity. And the techniques that we use for main memories is the double data rate DDR, which offers large capacity but limited bandwidth, typically around 50 to 100 Gbps. For more demanding workloads like AI training, we see high bandwidth memory or HBM, which can deliver over a terabyte per second by sitting very close to the GPU die. And GDDR is commonly found in gaming and inference GPUs. They also provide high bandwidth with moderate latency. And another technology we rely on is the unified memory systems, such as NVIDIA's UMA or AMD's Unified Address Space. They simplify the programming by automatically managing the data movement between CPU and GPU memory because they share the address space. However, in non-uniform memory access systems or NUMA, with multiple CPU sockets, data placement is critical. If data is accessed from the wrong socket, it incurs very large latency penalties. Overall, while this segmentation helps optimize for different workloads, it also increases the cost of data movement. The latency, the energy consumption, and the latency of communication, the energy consumption, and the bandwidth bottlenecks are now the major challenges in scaling HPC and AI workloads efficiently. And when we talk about the interconnect technologies, the goal is to enable fast communication across thousands of nodes and GPUs because network bottlenecks can make or break the scaling efficiency. InfiniBand is the long-standing HPC standard, which offers very low latency and high throughput, which is why most supercomputers rely on it for MPI-based applications. For GPU clusters, we have the NVLink and NVSwitch from NVIDIA. They play a critical role. They provide extremely high-speed GPU to GPU communication inside a server, reducing the data transfer overhead during a distributed training. On the other hand, Ethernet with RDMA or the remote direct memory access is emerging as a cost-effective alternative. It can deliver near InfiniBand performance, but at a lower cost, making it attractive for large-scale AI clusters. Finally, topology awareness is important. The way GPUs and nodes are wired, whether it's in a mesh, a torus, or a factory network, it directly impacts the MPI collectives and the distributed training performance. So optimizing communication for the underlying topology is the key to getting the best scalability out of an HPC system. And in HPC system, the storage is just as critical as the compute because large simulations and AI training generate massive volumes of data. So we have parallel file systems like Lastrade, GPFS, and BGFS. These are the standard supercomputing. They stripe the data across many disks and servers so that thousands of nodes can read and write simultaneously. And to reduce the I/O latency, many systems also deploy burst buffers, which is an SSD-based storage layer that act as the fast intermediaries between compute nodes and the slower parallel file system. So this is especially useful for checkpointing or capturing short-term high-volume outputs. So another approach is tiered storage, which we just discussed, where the hot data that needs fast access is kept on high-speed media, while the colder, the less frequently accessed data is pushed to the cheaper, slower storage with high capacity. But it is important to note or remember that I/O bottlenecks are often the silent killer of HPC performance. So you can have the fastest processor and GPUs, but if your storage system cannot keep up with the data movement, the overall performance will collapse. So this makes the efficient storage design a key part of any HPC architecture. Okay. Now that we have covered the fundamentals of HPC architectures, let's shift our focus. The landscape is rapidly moving towards AI accelerators. So these specialized processors are designed specifically for the massive parallelism and high bandwidth required by the modern AI workloads. So in this deep dive, we'll cover the main AI accelerators, the GPUs for the mainstream training and inference, FPGAs for reconfigurable workloads, CGRAs for a balance of flexibility and efficiency, and ASICs like Google TPU for maximum performance per watt. So first, let's see the GPU. As we can see in this figure, a GPU is made up of many streaming multiprocessors, and each streaming multiprocessor SM contains a group of CUDA cores or streaming processors or tensor cores, register file, and shared memory. And each SM, or you can think of an SM as the basic building block of computation inside the GPU. And this each of these SMs can manage thousands of lightweight threads at once using SIMT because they are made up of multiple SPs. So this figure actually highlight why GPUs have become the workhorse of AI and HPC. Because unlike CPU, we have a handful of powerful cores, and GPUs pack thousands of such cores which are designed for highly parallel workloads. So that makes them ideal for the kinds of tensor and the matrix operation, which are the heart of deep training. So they also provide extremely high memory bandwidth, often using HBM, which is crucial for keeping those cores fed with data when required. So as a result, they are the best choice for training large-scale AI models, running inference efficiently, and even accelerating scientific simulation that will require massive parallelism. But if you need a reconfigurable option, we have the FPGA, the field programmable gate arrays, which is actually a reconfigurable hardware. Their fabric is composed of many configurable logic blocks or CLBs, and that are wired together to implement custom data paths and control logic. So unlike CPUs and GPUs whose architecture is completely fixed, FPGAs let you tailor the hardware at the granularity of these CLBs to match a specific model or even a critical layer within a network. And the interconnects between the CLPs, which are made up of programmable wiring and a switch matrix, that itself is reconfigurable. So you can optimize the data flow and reduce unnecessary data movement by laying out computation where data already resides. So because of this fine-grained control, FPGAs often deliver lower latency and deterministic performance compared to GPUs, even though their peak throughput for large dense workloads may be lower. So that combination of reconfigurability, low latency, and pretty good energy efficiency makes FPGAs especially useful for edge AI, real-time analytics, or streaming inference and other low power, low or latency sensitive deployments. So another solution which comes midway between FPGAs and ASICs is CGRA, which is the coarse-grained reconfigurable array architectures, which is essentially an array of processing elements which are connected to each other, and even the interconnects are reconfigurable, and each processing element will house a functional unit like an ALU or a maxtail unit with a local register file or buffers, and interconnected by programmable routing network. So hot loops or data flow graphs are compiled and scheduled so that operations can stream from P to P because they are connected to each other, enabling deep pipelining and high on-chip data reuse. So this minimizes the off-chip memory traffic and greatly lowers the energy per operation. And one advantage of CGRA over FPGA is that the FPGAs have a fine-grained overhead where this CGRAs are giving a word-level reconfigurability. So that will save us much more energy and can give much more deterministic latency on regular and compute-intensive kernels like the gem loops or the convolutions and stencil code. But the trade-off is the toolchain complexity. So the compiler will be very complicated for the CGRA because we need to map our operation nodes to the processing elements. It's not just one unit. So to each process, we should correctly identify to which processing element we can assign an operation from where I'll get the data for my next computation. So the toolchain complexity is a bottleneck there, and they perform, and coming to the applicability, they perform based on structured and loop-centric code rather than highly irregular algorithms. So in practice, these CGRS are well suited as on-chip accelerators or card accelerators for edge and embedded AI, where high performance per watt and low latency matter. Now comes the ASICs, the application-specific ICs. These are custom chips built to run a narrow set of AI operations extremely efficiently, great performance per watt, but low flexibility. So a popular example is Google's TPU, which centers on a large systolic matrix multiply engines or MXUs that stream tiled activations and weights through arrays of max cells, backed by on-chip scratch parts or unified buffers, and DMA engines to minimize the off-chip traffic. So the TPU ports connect many such chips over a high bandwidth, low latency fabric to speed the distributed training, while the compiler map the model graph to the MXUs and memory hierarchy to maximize the data reuse. So that's all about the AI accelerators. Now let's switch gears to the big picture, the architectural trends for scalable AI. I'll cover 5 key trends here: the heterogeneous computing, domain-specific architectures, which are tuned for tensor math or energy-aware designs that cut the data movement. Next is the energy-aware design, the composable HPC, and the converged HPC AI and analytics platform, where we unify all these together. Let's see the heterogeneous computing first. So the reality in modern HPC and AI is that we rarely rely on one class of device anymore. Instead, systems combine CPUs, GPUs, FPGAs, and ASICs and orchestrate them to get the best performance per watt for each part of the workload. We already covered the device roles. Here is how they are being combined strategically. So here, in heterogeneous computing, CPU remain the general managers. They handle the control flow, the pre-processing, the orchestration, and the irregular tasks that don't vectorize well. On the other hand, GPUs and other accelerators will take over the dense data parallel work like big matrix multiplications, convolutions, and other tensor kernels. And FPGAs and CGRS are used where low latency, reconfigurability, or specialized data paths is a concern. And ASICs are used when the workload is stable and you can justify the fixed silicon investment. And the common real-world stacks often combine, let's say, an excited CPU, multiple HBM-occupied GPUs, which are connected by NVLink or NV switch, then an optional FPGA or smart NIC for in-network reduction or compression. And when we talk about exascale class AI, this heterogeneous mix is a mandatory or the default thing, not a choice. Okay, so because heterogeneous stack rely on specialized engines, that leads naturally to the rise of domain-specific architectures like NVIDIA Tensor Cores and Google TPUs. We don't go deeper here since we have already discussed their concepts and applications. So the next 3 trends are intertwined. The energy-aware design addresses the cost of moving data. The composability or the disaggregation changes how resources are provisioned, and the converged platform will unify the workloads to reduce the data copying and friction. So let's see the energy-aware design. Actually, or empirically, the data movement costs far more energy than computation. So modern designs prioritize minimizing the off-chip transfers by employing techniques like near memory compute or even in-memory compute, larger on-chip buffers, HBM stacks, and in-network aggregation. Examples are HBM processing in memory or PIM, smart NICs that perform reductions, and DMA engines that can prefetch and fuse the transfers. And on the software side, we have compression, sparsity exploitation, and operator fusion that reduces the bytes moved and the energy consumed is reduced. Coming to composable HPC, here disaggregation means we separate the CPU, the GPU, the memory or the other storage unit into resource pools connected by a fast fabric. And the idea is to compose a node on demand for a job. Example, like allocate an extra GPU tile or a remote large memory slab to train a job when required. So this will improve the utilization and also avoid statically over provisioning expensive GPUs. But the challenge is latency and bandwidth across the fabric. For the composability to work, we need to have the fabric to work very fast, or the use case must tolerate some remote access cost. So next is unifying or converging the HPC, AI, and analytics together. Which means we are collocating the simulation, the model training, and analytics on the same infrastructure. So this will remove the data egress and ingest overhead. Okay, by egress overhead means moving the overhead incurred in moving data out of a computing node, and ingest means the overhead in moving data into the computer nodes in case of distributed training. Okay, so by unifying this, we can get rid of such overheads and also enable tight feedback loops. For instance, when we run an AI model that steers simulation in near real time, we can have this all unified, and without incurring all these overheads, we'll get the ideal runtime. So convergence minimizes the pipeline friction and also improve the end-to-end time to insight, but it requires careful resource orchestration. So that's the challenge there. An example is NVIDIA's Earth 2, the weather forecast solution by NVIDIA, and another is by AMD's El Capitan. And together, all these trends push us to think holistically. So when we design or choose an HPC system for our AI workload, the question we should ask ourselves is, does it minimize the bytes moved, or does it compose the resources on demand and support the dominant compute patterns of my model? So we should ask that question and choose wisely. So that's the key here. Now, moving on to the core topic, scalability and performance modeling. So the scalability can be viewed in two ways: strong scaling and weak scaling. Strong scaling will keep the problem size fixed, but will add more processing unit so that we can reduce the runtime. So the workload or the workload assigned to one processing node will be reduced by the factor of the number of processing units added. That is, TP will be equal to T1 by P, where or the time which we will the performance will be governed by this equation TP equal to T1 by P, where TP is the enhanced runtime, and where T1 is the original runtime and P is the number of processing units added. For example, if we train the same data set faster with more GPUs, we keep the data set size fixed. So that's the idea of strong scaling. But the issue here is that the Amdahl's law shows that even a small sequential part can limit the maximum speed up, which means, let's say if we have uh, P, or let's say N number of processing units added, and the fraction of the program that is getting parallelized is, let's say, P, then the maximum speed up which we can achieve by adding N number of processing nodes is the maximum is 1 by 1 minus P plus P by N, because it is the serial part that limit the maximum speed up achievable. So even if you have hundreds of processes, the serial fraction becomes the bottleneck. So that explains why adding more GPUs or CPUs eventually yields diminishing returns. You might have noticed this in your experiments as well. So for strong scaling, while we keep the problem size fixed, we will definitely hit this Amdahl's law walls. Coming to weeks, okay, I have a graph also. We'll see that in detail when we move on to the demo part. So here we see that, let's say P is the fraction of the work which we parallelize. P equal to 1 means it is entirely parallelized. Then we'll get a speed up proportional to the number of cores or the number of devices we added. It's a linear curve, but as the fraction of serial portion increases, we'll start seeing the diminishing effect even by adding number of cores. It is flattening very early, like it is going to a saturation point here, because it is limited. The achievable speed up is limited by the serial fraction of the work. But when we go to weak scaling, so weak scaling means as we add more processor, we also grow the problem size, aiming to keep the runtime roughly constant. By that, we'll be able to get the overall speed up increasing or proportional to the number of devices we added. For example, in climate simulation, adding nodes let us simulate a larger domain without increasing runtime. So the per node workload will remain constant. That is, TP will be equal to T1 for a particular node. So this is where, do we have any bottleneck here? Not exactly. That's what Gustafson's law says. It shows that when the workload scales with resources, speed up can be nearly linear, because the speed up attained, in Gustafson's terms, the speed up that can be attained is n minus alpha into n minus 1, where n is the number of processing units we add, and alpha is the fraction which is serially getting executed, which is a 1 minus p in the case of Amdahl's law. So it is giving a near linear curve. And this, see, if we see this, we should say that it is closer to the real world AI workloads. Because in AI training, we often scale the batch size, the model size, or the data size. So the Gustafson framing is more realistic for large AI workloads, which continue to benefit from bigger scales. Okay, now that we have seen that with weak scaling, we can achieve the near linear speedups by adding in more nodes. But that works in theory. But let's talk about why the performance often falls short in practice. We do have bottlenecks. As mentioned earlier, one of the biggest reason is the communication overhead that kicks in as we add more devices. So the distributed system will require frequent data exchange to stay synchronized, and that becomes the major bottleneck. For instance, let's say the MPI collectives like all reduce or broadcast are widely used in AI training and HPC workloads. But as the number of nodes increases, these operations gets more expensive since they involve many-to-many communications. Is that a question? Okay, maybe not. Okay, so we are saying that as we increase the number of nodes, the communication, the many-to-many communication will also be involved, and this communication can bring in an overhead there. Similarly, like data transfer over NVLink, they are much slower compared to the on-chip memory access So moving large tensors or gradients between devices can quickly dominate the execution time. And at the cluster level, the case is even more serious because the network contention and the latency can further add delays as multiple nodes are competing for the bandwidth. So in practice, this means that at larger scales, the bottleneck shift from pure computation to how efficiently data can be moved around, which is why modern HPCs invest heavily in high bandwidth, low latency interconnects like InfiniBand or NV switch or custom fabrics. We'll see the effect more clearly in our demo section as well. So another bottleneck is the load imbalance, where some processors finish early and sit idle while waiting for the others, which is especially common in distributed AI training during gradient updates. We also face synchronization cost, barriers, waits in tightly coupled tasks that stall the progress until everyone catches up. So to mitigate these issues, we use techniques like overlapping communication with computation. Like we try to mask the communication overhead with computation by carefully tuning or partitioning the domain or the tuning the partitioning or by carefully decomposing the domain and adopting asynchronous execution model. So these strategies help us get closer to ideal scaling. Okay, next is the performance energy cost trade-off, which is a crucial element in any architecture or any solution. So when designing HPC and AI system, it's important to balance performance, energy, and cost. So on the performance energy front, techniques like DVFS, like dynamic voltage and frequency scaling, that can reduce the clock speed to save the power with only a slight performance loss, while specialized hardware can deliver much higher flops per watt, like the ASICs. And the performance versus cost requires careful planning because the cloud GPU hours may be convenient but expensive, whereas on-premise clusters have high total cost of ownership. So over-provisioning resources to meet deadlines can improve performance but increase cost. Self-explainable. And the energy versus cost, that's also critical, as power and cooling often dominate long-term operational expenses. So metrics such as flops per watt or joules per iteration and dollars per training they'll help quantify this trade-off. So finally, we sustainable HPC initiatives like Green 500 ranking or renewable power data centers are increasingly influencing these design decisions. Okay, moving on, we'll see how different programming models help us unlock the full potential of heterogeneous HPC and AI hardware, because even we are given the best hardware on earth, if you're not able to harness the power or exploit the most of the hardware by using the software, it's of no use, right? So we'll see the HPC programming models also quickly. MPI, the message passing interface, that's the widely used standard for distributed memory HPC, providing point-to-point and collective communication across nodes. And for shared memory parallelism on CPUs or accelerators, OpenMP enables thread-level parallel loops and tasks, including offloading to GPUs. And on the GPU side, CUDA is NVIDIA's framework with explicit kernel launches and memory transfers, supported by libraries like QBLAS or QDNN and NCCL. And AMD's counterpart is ROCm, which uses the HIP API for CUDA portability and provides libraries like ROC BLAS, MIOpen, and RCCL. Finally, we have the CCL, which offers a single source C++ programming model for heterogeneous hardware, which means using the same programming language, we can program for multiple machine or architectures like CPUs, GPUs, and FPGAs. So one popular example is Intel's one API DPC++. So together, these models let us exploit all levels of parallelism, from threads to nodes to accelerators. So when training AI models at scale, specialized distributor frameworks make it easier to leverage multiple GPUs and nodes. One example is Howard, from Uber that uses MPI backend and implements ring or reduce to efficiently synchronize the gradients across workers. And next is a deep speed from Microsoft that introduced Zero Optimizer to reduce the memory usage and support both pipeline and tensor parallelism. Another is the Megatron LM from NVIDIA that focuses on large-scale transformer training, combining the tensor and the pipeline parallelism for massive models. So other options are like PyTorch DDP, which provide built-in data parallelism and rate train. That helps in orchestrating the distributed training workloads, which is very critical, as we mentioned already. Okay, together, these frameworks will simplify scaling the AI workloads while addressing memory, compute, and communication challenges. And from the compiler side, we have techniques like vectorization that enables simmed execution using AVX or SVE instructions. Uh, and we have loop tiling and loop unrolling that will improve cache reuse. Or we can apply function inline that will reduce the function call overheads. And there are auto tuning tools like TVM or OpenTuner that will optimize the kernels for specific architectures. And see, the typical workflow is to profile the application and find the bottlenecks. So for we rely on profiling tools like MuProf for AMD CPU and GPU counters, and for NVIDIA, and we have Nsight systems and Nsight Compute for GPU timeline. And there are CPU level tools like Perf, VTune, and Liquid. And for large scale, we have a TOE and HPC toolkit that will provide a detailed profiling. And as said, the typical workflow is to first profile the application to find the bottleneck, then apply the targeted or perform the source changes. And so with these concepts in mind, let's move to the demo and see how these HPC fundamentals translate into real AI speedups. So in this demo, our goal is to model how an HPC system scale for an AI workload. We'll use a lightweight portable simulation environment in Google Colab with Python, NumPy, and Matplotlib. And the key parameters include number of compute nodes, problem size, and bandwidth paralleling. We'll explore both strong scaling and weak scaling. And the outputs will show the execution time versus nodes, the speed up curves, and the breakdown of performance bottlenecks, letting us see how parallelism, communication, and hardware features will impact the real AI performance. Okay, let me move to the, let me stop share this and share my column. Okay. Okay, in Google Colab, we have access to T4 GPU, which is good enough for our simulation for this micro benchmarks, which I'll be showing now. So let's connect to this T4 GPU. And okay, let it connect. Okay, so now let's do a sanity check. Okay, so here it shows that the CUDA is available and the GPU name is Tesla T4, which means the connection is perfect and we have a CPU, a dual core CPU. Okay, now let's move into the all that we see in the concepts. Let's see in in graphs. Okay, let's first talk about the strong scaling versus weak scaling. In strong scaling, we said we'll be keeping the data size fixed, but we'll add more processing elements or devices and to increase the speed up. But we also saw that Amdahl's law, as per Amdahl's law, the speed up is limited by the serial fraction. So let us model that with uh, P being, we are setting P as 0.95, which is the parallel fraction of for the Amdahl's law for strong scaling, and N is the number of cores. We will be taking the number of processing elements or devices. So I'm adding a range of 1 to 129, and for the to see how it affects the weak scaling, and we'll be modeling the Gustafson speedup as well. So for that, we have alpha, which is the serial part for Gustafson. So I've set it as P as 0.95 for strong scaling and alpha as 0.05, which means the split is pretty much the same. So we are going to model this Gustafson and Amdahl for 1 to 120. Hello.
Might be a noise, Chilanka, you may continue.
Okay. Okay. Thank you. All right. So, okay, I have just pre-run to avoid a last minute glitch, but let's run it now. Okay. So this is the curve that is plotted with the Amdahl's and the Gustafson speed up curves. So the parallel workers, we have 0 to 129, 1 to 129. And on the left side on y-axis, we are showing the speed up. So let's first focus on the Amdahl's curve. See here, we see that as we increase the number of devices or the parallel workers, the speed up is increasing, but very slowly, and it attaining the saturation point very early. So it is like a very flat curve, which means even though we are adding, let's say from here, even though we are adding the devices from 80 to 100 to 120, there is no effect on the speed up curve because it is limited by the serial fraction of the workload. Whereas if we see the Gustafson, as we increase, Gustafson corresponds to the weak scaling, where as we increase the number of parallel workers, or as we increase the number of devices, we are also increasing the data size. So it is scaling near linearly. So we see that it is a linear progression that we see in Gustafson. As we add more nodes, we are seeing the speed up is also increasing proportionately. But let's try increasing the parallel fraction of Amdahl's law. Let's say make it to 0.99. We'll see that it is going up, moving closer to the linear, because now the serial fraction is minimized to 0.01%. So that's why we are seeing some improvement. So anyhow, we understood that it is limited, or the speed up or the maximum speed up achievable in strong scaling is limited by the serial fraction, and in weak scaling we can achieve whatever speed up, the overall speed up, because we are now considering multiple workloads or increased size to work. We can attain high speed ups with weak scaling. So in the next session, what we see is the impact of programming models, keeping a single node. Okay, let's say we have only one node, we are not able to add in more processing units, but we do have our programming models or the compiler techniques. Let's say we have here we are comparing the results with Python, NumPy, which can generate vector code, and NumPyJit, where it can generate near native code, like the near assembly or the closer to machine code. And we also see the multiprocessing, like the how multiple threads can help us improving the or reducing the runtime. So here the microbench I have included is simple multiplication and additions. This is it. AI into BI plus CI. So this is how the pure Python will do it with a 2-level nested loop. And NumPy, it can work with vector codes, and so it is preparing sum of A into B plus C instead of the scalar operations. And for NumBudget, we just give the same code, but it will be able to generate the near native code. And in multiprocessing worker, what we'll do is we will break the data into chunks, and each chunk will be taken up by each thread in the multiprocessing environment. So the size, I'm actually increasing the size of the data size and showing how each of these programming models can help us by increasing the size. And we started with 100,000, 1 million, and 5 million. So we are plotting the runtime. Okay. Okay. So these are the output. What is given in the tables is the runtime in seconds for the data sizes 100,000, 1 million, and 5 million. So this first column is the N. And the next column shows the results with pure Python. Next is with NumPy. And the other is with NumPyJIT. And next is the multi-processing environment. The course is kept as one. We haven't increased any processing units. But we see that if we come, let's take the first one, the size 100,000. If we compare this data, we can see that the maximum time is taken on for the multiprocessing environment, where Python could have a more optimized code, and NumPy, which could generate the vector code, and NumPy is having the highest performance because it could generate the near native code. So we'll see that. Okay, and we'll also see how that scale with the size, with the input size as well. Okay, so this is for pure Python. As the problem size increases, we had a much steeper curve, and later it is increasing in a slower pace. And NumPy, same, but much earlier it could start increasing. And for NumPy, it is more of a straight line kind of. And multiprocessing, yeah, it is near like linear, but the problem is the time we took is much higher compared to the other programming models. So that's how we compare the different programming models or the compiler support. So then what we can say is that whenever we don't have multiple nodes available, we can better go for NumPy, where we can generate vector code. But so here we saw for NumBudget, it is showing better performance, but then mostly when the data size is higher, it is the vector code that will give you the better performance. That's the usually that's what we see here. But here the speed up is much more in NumPy. But usually, as this is just a fabricated or it's a micro benchmark, so whenever possible or vectorization is possible, it's better to go with NumPy. Otherwise, if vectorization is not possible, well and good, we should go for the NumBudget. And if nothing of these sorts are available, then the multiprocessing environment can help with. Now let's see the communication overhead, which we discussed conceptually. Let's see. So here we are discussing how the ring or reduce will the MPA collective ring or reduce work. Okay, so in ring or reduce, what it does actually is we are splitting or distributing the training operation across multiple nodes. Okay, so for that, first of all, the split data, the input data needs to be sent to each of the nodes. So there requires some communication overhead, and once all these individual nodes have done their processing, the results needs to be reduced. So it will be sending, one node will be sending to its neighbor, and there it will be reduced, and the reduced result will be sent to its next neighbor, and so likewise, and finally we get the final reduced result. So that's how it works. But you can assume how much communication is happening there. First of all, to send the input data. So to scatter, we have some communication overhead included, and later the result is need to be gathered. So there is communication cost in both sides, and therefore the entire time that taken for computation is now reduced. Of course, the computation time is reduced because we have added more compute nodes. So per node workload is less, therefore the runtime is less there. But it's not exactly divided by the runtime is not exactly divided by the number of processing units, but we need to add in the communication cost also. So it depends on the latency, which means latency means the latency of the communication latency, the bandwidth of the interconnect, and the message size, and the number of device counts. So this is the equation for the ring or reduce time. It's 2 into p minus 1 into alpha, where alpha is the latency, p is the number of processing units we add, and m is the message size, and b is the bandwidth. So here we are doing it, and let's plot it and see. Here we are plotting the final runtime for multiple, or by adding more devices across different bandwidths. Let's first take the blue line, which is corresponding to a bandwidth of 5 Gbps. Here, as we increase the number of devices, the runtime is shown to be increasing, and then it reaches to a saturation point. So this all reduced time is actually dominated by the communication overhead time. So as we have more number of devices added, the communication cost also increases, because those many communications needs to happen. So it will definitely increase, but later it will reach to a saturation point, and the same trend is seen in the other bandwidths as well. But with higher bandwidths, we are seeing much lesser all reduced time, because we have higher bandwidth. Obviously, we'll be getting the lowest or the least runtimes with the highest bandwidth, but the trend remains the same. So as we increase more devices, the communication time will increase, but later it will reduce. It will reach to a saturation point. Therefore, it's okay to increase more devices, because the communication time will not increase after some threshold point. And let's see the per device effective throughput. Throughput in the sense how much bytes are transferred by each device. That is the effective bytes per second per device. So that's actually the amount of data that needs to be communicated between neighbors. So that's what we have plotted on the y-axis, and on the x-axis we see the number of devices. So let's focus on the highest bandwidth. Let's say the green line, which has the 50 Gbps bandwidth. So we start with 2.5 bytes per device, because let's say we're talking about message size. Let's say the message size is 100, and as we have only 2 devices, so the message that's to be transferred will be large. But as we increase more devices, so it will be divided into chunks and distributed among the nodes, and therefore the data to be transferred between neighbors will also reduce, right, by the fraction of the devices we add. Okay, so that's what we see. It reduces like it falls like very steeply as we increase the number of devices, but as we increase more devices, even that point or the even that becomes a or comes to a saturation point. Here even the bandwidth doesn't matter, because as we increase more devices, the data or the communication or or the packet that needs to be sent in between is split into smaller and smaller chunks, and there is a basic bytes per second that each device will inquire, even if however smaller chunks we finally attain to. So here even the bandwidth of the link doesn't help us here. So that's what we see in this communication overhead. And in the next session, we'll see an AI mini training where we fabricate one data set and a small CNN, making use of QDNN, the library by NVIDIA. And here we will compare different techniques like mixed precision. Mixed precision, we have seen that AI workloads doesn't need double precision accuracies, right? So we can work with FP16 or even in 8. So that will help us reduce this memory requirement or the memory bandwidth requirement, and even the computation time will also be less if you're working on a lesser precision data. Therefore, the mixed precision is one way to get high throughput on GPUs. And we also work with the data loader is also pre-tuned, like we're adding more workers, like to load the data, we are adding more workers so that GPU doesn't have to wait for so long. So that is one way. Another is the pin memory impact, where GPU can use a DMA for the data transfer. So we'll include all these techniques and we'll compare the result against the baseline CPU. But as you know that if you compare the same data size performance for CPU and GPU, we can't put it in a simple graph without scaling. Therefore, what we do is like we are also increasing the data size also and putting in a single curve graph. Okay, so here we prepare the CNN, here we prepare the data set, and then we are setting different configurations. So the different configurations we use is, first is the CPU baseline, where no GPU is used, no AMP is a mixed precision technique is not used, and the number of workers, the data load workers is also not used, and the batch size is 128. In the next setup, we are using GPU instead of CPU, but we are increasing the number of data load workers to 2 and the batch size to 512. And in the next competitor is GPU with AMP, and the number of workers remain the same, but the batch size is increased to 1024. And the next candidate is using all these together, like GPU plus AMP plus the number of workers also increased, and we are increasing the batch size as well. So let's see. Okay. Maybe I don't have to run it since it will take a little time here. So let's move on to the results. So this is the graph where we plot all these, where we have the CPU baseline. So even for a smaller batch size, it is taking this many seconds for just for 2 epochs. And on GPU without AMP, the time taken is much less than CPU for a higher batch size data. And with AMP, you see the difference between by using a lower precision data, how much speed up can be achieved on a GPU. See, even by increasing the batch size from 512 to 1024, the runtime is we are getting is 2 times or speed up even for an increased batch size. And for GPU with double the batch size, but with double the number of data load workers, we are able to achieve the same runtime. So this is how different techniques help with help with the AI workload runs with GPUs and other techniques used. Okay, let's go back. Okay, so now we have seen how to bring the HPC fundamentals to AI scalability. So here we saw that speed up is bounded by the serial work by Amdahl's law unless we scale the problem or increase the problem size. And single node efficiency, we can prefer vectorization or no budget over row loops and avoid over parallelising tiny tasks. And for distributed limits, latency and bandwidth define the scaling ceiling. We have seen that in the ring all reduced model. And when we use GPUs, use mixed precision, large batches, and data loader tuning by adding more workforce there and kernel auto tuning, we can achieve the performance what we aim for. So the practical workflow is we'll first set up a configuration. We'll first have a setup done. Then we'll measure. Then identify the bottleneck. Then we tweak each of the knobs and then remeasure and reiterate. So that is the practical workflow for when we use HPC for AI workloads. Okay. Now let's see what is the shape of industry landscape in HPC AI accelerators. Okay, we have a rich set of AI accelerators. Like NVIDIA remains the dominant force with GPUs optimized for tensor and matrix operations. It has the deep CUDA integration, high bandwidth interconnects like NVLink, which make them ideal for large-scale AI training. And AMD is catching up with its MI series accelerators, offering HBM memory capacity, high bandwidth, and open source ROCm stack as an alternative to CUDA. Intel is also active in both GPUs like Ponte Vecchio for the Aurora supercomputer and specialized AI accelerators such as Gaudi, which leverages Ethernet fabric for distributed training and inference. And we have the ARM-based processors in HPC and cloud AI, like the Fujaku and the AWS Graviton processors, which include machine learning instructions for AI acceleration. And beyond traditional GPUs, ASICs like Google TPU also excel in fixed function AI workloads. And we have Cerebras that push the wafer scale architectures to minimize communication overhead. We have CGRs, though niche, are promising for loop and data flow heavy workloads, offering both flexibility and efficiency. So overall, the industry trend is moving towards heterogeneous system that mix the accelerators to balance the performance and energy efficiency and workload specialization rather than relying on a single one-size-fits-all solution kind of a policy. So what is next? So looking ahead, the HPC for AI is being shaped by several next-gen trends like exascale AI, like the Frontier and Aurora that provide enormous computational power, enabling near real-time training of massive AI models on huge data sets, which is critical for applications like scientific simulations and LLMs. And the quantum computing is beginning to play a role in HPC, particularly for specialized tasks such as combinatorial optimization and molecular simulations. And there are often, even though fully general purpose quantum compilers are not widely available, these systems are often accessed through cloud or hybrid HPC quantum steps. So next is the photonic computing, which uses light instead of electricity for data transfer and computation. That also promises significant reduction in latency and energy consumption, which is making it attractive for communication-heavy AI workloads. And then we have the neuromorphic chips, the brain-inspired architectures like the Intel Loihi that mimic the behavior of neuron synapses. And finally, we have the edge HPC convergence, where AI workloads are split between central HPC clusters for heavy model training and edge clusters for latency sensitive applications like autonomous systems and IoT devices. So together, these trends are indicating a future of highly heterogeneous, energy efficient, and specialized computing platforms that will allow AI to scale both in size and responsiveness across a wide range of applications. And we can't wind this up without talking about sustainability. Energy is now the first class design constraint. We should go for energy wise scheduling, and we do have cooling that shift from direct liquid and immersion, reducing the fan pump energy and other enabling denser nodes and renewable sources, like where we can scavenge energy, like the European supercomputers are running on hydro and wind, and the data movement is the for to reduce the data movement. We are by reducing the data movement itself by incorporating techniques like in-memory and in-memory processing. We are reducing the energy heavy transfers. Okay, so let's wrap it up. So we have seen that HPC plays a critical role in AI and data processing, enabling workloads to scale well beyond single node limits. And the key architectural components include CPUs, GPUs, specialized accelerators, high-speed memory, and interconnects, and all of which contribute to performance. We have seen important scalability concepts like strong and weak scaling and how to identify the performance bottleneck. And on the software side, programming models such as MPI and CUDA, along with distributed frameworks, compiler optimizations allow us to make the most out of the hardware. And looking ahead, trends like heterogeneous computing, domain-specific accelerators, the focus on sustainability will continue to shape the future of HPC for AI workloads. All right, so that brings to the end of our session. I encourage you to check the reference page for more details and let me know if you have any questions. Or if not now, you can write to me as well. So this is my email address. Let me know if you have any question.
Okay, any questions from the side of the participants? I think there are no more questions. So thank you, Dr. Chilanga, for sparing your time, for sharing your insights in the area of high performance computing. It has been really a fabulous session, and we all know that the area of high performance computing, that's an area that is normally ignored in the flood of AI technologies. We have AI algorithms, ML algorithms, various AI techniques. All these are there, but we normally ignore the case of high performance computing and how scalable these architectures are to be for the sustainable development of AI. And it has been a great pleasure to watch you take a session once again. Not to the faculty of Department of Computer Science and Engineering, but to the various faculty from all over India. And from the side of Department of Computer Science and Engineering, Rajiv Gandhi Institute of Technology, I would like to extend sincere thanks to you. And we would like to have you as resource person in our future faculty development programs and other sessions also. Thank you.
Thank you, sir.
Thank you very much, Dr. Chilanga, for accepting our invitation and taking a session for us. Thank you very much. See you again in the department activities. Okay,
thank you. And thank you, sir. And it's an overwhelming experience for me to see both of you as well. Okay. Yeah.
Okay, thank you.
Thank you for inviting. Many thanks, and to all of you for your attention. I hope you found the session useful. And since we have time, let me share one more bite. As Dr. Shibu mentioned, I work at AMD as MTS, and currently I focus on the CPU domain, where I work as a performance analyst, proposing a microarchitecture-based optimization for our in-house compiler AOCC, as well as open source tool chains such as GCC and LLVM. And as you may have seen from Dr. Lisa's post on LinkedIn, AMD is now contributing more actively to the AI space. So within the software systems domain, a key part of our work is now improving how compilers generate code so that data and compute-intensive AI workloads can run faster and more efficiently on our machines. So if any of you or your students are interested in this area, please feel free to reach out. Okay, thank you.
Yeah, thank you. Thanks.
Sir, I can leave.